Last talk of the day is by Professor Flicker, who is going to lecture on counting local systems with the principal unipotent monodromy.
I wish to thank I should wait for a Florian. So I would like to thank the organizers for the invitation and for organizing this very interesting conference. And I would just try to write one formula, and it will be computing a certain number of objects, and I'll try to first describe the objects, then write the formula in various ways, and the work is joined with the lin, and it goes like this. So first notations, I have a smooth, a projective, absolutely reducible curve over the field, over a finite field, Q elements, and let's say that the genus is G. And I'm fixing a finite set of closed points of this curve X. And there'll be some conditions on this later on, such as the cardinality of this set will be at least 2. The number of these closed points on the curve will be at least 2. And just a question of notation, sometimes I'll write x minus s, and sometimes I'll write x outside of s for the affine curve. And
not necessarily FQ rational.
These are FQ rational.
Yeah, but I did not
He
hear that.
didn't answer, but it doesn't
No,
matter.
but these are not geometric points, but these are points, closed points,
Yeah.
just closed points. So over an extension, they may split. And this will turn out to be important later on, that I have closed points, at least 2 of them. Then just notations. I'm looking at the function field. Let me denote it by F. So and so just let me write Fs for the maximal extension of this function field, which is unramified outside the places S. So, and this takes place in some separable closure of the field S, of the field F, so in this F bar. Okay, so we have these things, and I'll also fix an algebraic closure, FQ bar of Q, of F, Q of the finite field, and this will be in the separable closure. And what else do I need here? The object that we are studying is the geometric fundamental group that everybody here knows about. Of the affine curve. So the x minus s, and so this was described several times in previous talks, but let me repeat this again. So I have the pi 1 geometrically. And I would also think about it as the Galois group. So I'll just write this several times. Okay, maybe I'll continue here. So I'll just describe it a few times following previous talks. So this is just the kernel of the arithmetic fundamental group, which is the Galois group. To the Galois group of over F, which is just the Galois group of the algebraic extension over FQ generated by the Frobenius. So what we learn from this is that we have that this Galois group, that is the Frobenius, acts on the set of isomorphism classes of representations of this fundamental group, the geometric fundamental group. So I'm looking here at the affine line geometrically. And these representations are what we are trying to count. So let me give a name for the number that I'm trying to compute. And so the number will depend on the curve, will depend on this finite set of places S, and we will be looking at n-dimensional representations. So this, I guess that I'm looking here at n, which is at least 2. So
when you say representation, what means representation?
I have to define which number I'm looking at.
Okay.
And I'll define it 3 times. So, so this will be the number of isomorphism classes of n-dimensional irreducible L-adic. So I'm taking L, which is prime to P. Representations, let me write rho bar of this geometric fundamental group. So, which is written there, of the affine curve, after we deleted this finite number of points, which is invariant under the Frobenius with a single Jordan block so it will be of rank n, a monodromy at each point of S. So this is the number of objects that I'll try to count, and let me just repeat the same statement 2 more times in a different language. And it is, so this number is the number of isomorphism classes of rank n irreducible local systems on the geometric curve again with principal monodromy. So principal local monodromy at each of the points of S. With principal unipotent monodromy, I want to say, at each of the points of the finite set S. So, and they have to be fixed by the Frobenius. So this is another way of description of the same set of objects, and let me just repeat the same description in slightly different words. So it will be the number of rank n irreducible local systems on the affine curve. So again, with principal unipotent monodromy, at each of the points in this finite set S, which are taken up to isomorphism and twisting by a character of this Galois group, or if you like, of the Frobenius. So I'm looking at this set of objects that you can view as local systems, or you can view as representations of the fundamental group. A monodromy means that we have here a Galois representation, which means that we have, when you look at a decomposition group at these places, you have a representation of the Wedelin group, which means that there is the SL2 factor, and the image of that is unipotent rather than a smaller thing. I'll translate it to one more language later. So this is the set of objects that I would like to count.
Is the number of such objects independent of L?
So this again?
Is the number independent of L? Are you notation?
Yes. As long as L is prime to P, which comes from Q.
I'm sorry, I can't see why the last two definitions are equivalent.
So on the one hand,
You have fixed by Frobenius here, and the has disappeared.
because I twist by a character of the Galois group. So the two are equivalent. But you can take any of the formulations, and eventually it will become automorphic forms. But
but maybe the question is, could it be that as a phi 1 x minus s representation, it is irreducible, and then when you restrict to
no, sorry. I think that we are looking at the geometric, always at the geometric, and then we take those which are either fixed by the Frobenius, or we take equivalence classes up to tensoring by a character of the Galois group generated by the Frobenius.
But so is it clear that in every isomorphic class of twists you have also an invariant? If it's clear, then it's
I'm
it's
looking
fine, but if
at equivalence class. Yes, I think so.
not. Also,
But
the intuition says, yeah, if it's
You can forget about the third formulation, it's not important. Let me write the answer. To write the answer, I have to introduce some notations. And the notations, I think the important formulation is that we look at n-dimensional representations of the geometric pi 1 up to equivalence and fixed by the Frobenius.
Yeah, but the story here is not so clear actually. Can you explain?
Then I prefer to erase it and leave it to the end. The expression that I would like to keep is the isomorphism classes fixed by the Frobenius.
José had two questions.
So the answer will be stated in terms of the values of the zeta function of the curve. So let me just fix the notations. I want to look at the action of this Frobenius on the cohomology, so étale cohomology, and this would look like a product because the genus is G, then we have G, two G factors, and I'll write them this way. And in the formula, the number HM would come in as well, and this will be just the cardinality of the Picard group FQM points. And this number is just the value at 1 of the numerator of the zeta function. And if I write XM for the extension of our curves of degree m, then this is the numerator of the zeta function. So the denominator, which is the cohomology in degree 0 and 2, is just these factors. And this polynomial that we have here has integral coefficients. Maybe I need a little more notation, so let's say the set of closed points. And if I take any place here, which is the same as the place of the function field, we'll have a residue field. And let me denote it by FQV so that I have a notation for the cardinality of the residue field. It looks like, so I define the degree of V using this formula, and what comes into the formula is this number, which depends on the set S of bad places. This is the greatest quotient of the number n, which is prime, to the degrees of V for every V in the finite set S. So this is the bad number. And sorry, I need one more annotation. And so I have a number, and the mu is the Mobius function which is if k is a product of r distinct primes or not. So we have this number. The value of this number from number theory is that if m divides n, then Cm happen to be the number of elements in the extension of degree n such that X generates FQM over FQ. A little bit of arithmetic. Okay, so I think that I have everything.
What is n of s?
I have n of s, and this is a divisor of n. If I'm looking at n-dimensional representations, in the formula I'll have to consider those numbers m which are prime to the degree of all of the v's or not. I'll write the formula right now, you'll see it in, and then I'll complain about the formula and try to improve it.
So when you write the greatest quotient of n, and then there's a blank, and then there's prime degree b, so what does that mean?
Greatest
Here-
quotient of further on in n of s.
So
In the definition of n
Of
of
n of
s,
s.
you wrote greatest
Greatest-
quotient blank of blank n prime degree.
greatest quotient of n, which is prime to the degree of v for every element in the set. So this is what I want to
Which is
compute. And the formula looks like this. It says that the number of these classes of Frobenius invariant representations of the fundamental group of degree n is given by a formula. This formula has in it a sign. Then there is the Picard number. Then there will be a sum over all positive integral divisors of the number ns, which divides n, of the number cm, some other numbers tm, minus 1. I just have to tell you what are these numbers tm. Again, although I didn't write it there, they depend on all of the data that we had before, and it is given by the quotients of these Picard numbers, m to the power n minus 2 divided by q to the n minus 1. I need a little more room, so I'll write it a product over j, which is between 1 and n over m. And here I would have the values of the numerators of the zeta functions at q to the mj divided by 1 minus q to the mj squared. And then I'll have a product over the set of places 1 minus qv to the power mj. So, sorry about the mix here. So there is some formula.
You say capital N?
Capital N appears here. That's the cardinality of S.
Ah, okay.
Ns is a divisor of n, and then there are these number theoretic things from the Möbius function, and Tm is given in terms of the zeta function of the curve. So, normally I should prove something also, but this I think will be difficult to do here, so I'll give you an exercise. And the exercise is, in the case that the genus is 0, okay, so the genus is 0, we then have that all of these functions are just 1. Simplifies life a great deal. Let's look at the easiest dimension, which is two-dimensional representations. And my condition was that the set S contained at least 2 elements. And let me assume for this exercise is that the sum of the degrees is equal to 4. The exercise is to compute the number t. The answer is q, and this is an elementary exercise that turned out to be very interesting. Maybe we'll get to it at the end to deduce something from it. So, the exercise is very simple, but nevertheless it requires just a tiny little bit of care, and that is that we have here many possibilities, like 1 plus 1 plus 1 plus 1, or 2 plus 1 plus 1, or 3 plus... There are many possibilities. And there is one case which is missing, and that is the case 4 is equal to 4. And if we get to it at the end, there is a question of how to prove the theorem in the case, this case, when n is equal to 1, which can be done by twisting of this situation. Okay, I want to consider also the number same as before, except that there'll be one more parameter. I want to consider the number of the fixed points of the iterates. So Frobenius to the power m, so these powers of the Frobenius. And when you look at the Frobenius to the power m, so it acts on our curve, and it is the so it is the Frobenius again, but for the curve replaced by xm over fqm. And so when you look at it from this perspective, then this number is just the number that we considered before for xm, but for the base change of the curve x to the curve xm, but also the set of points which are closed points, they may split. And the problem is that the number that we have here depends on s. So it is not clear from the statement that I wrote here that when you, the m here and the m here have nothing to do with one another. So the question is, what would happen if I want to consider the base changes of the curve x to higher base fields? And how would this formula vary with it? So what I want is to get a formula which is analogous to the Lefschetz fixed point formula, in which we would see here a virtual sum of powers of Weil numbers. So the question is how to formulate it and how to see it. So I need a few more notations. Not much, but let me write eta v for the collection or the set of, let me write dv for the degree of v. I'm not sure it saves much, but I'm looking here at the roots of unity, and let's write zeta or zeta m for the mth roots of unity, and I need to replace the collection of the eigenvalues of the Frobenius with the lambdas which are written up there. I have to change the sum a little bit to make it compatible with base change. So let me write B for the multiset, so set with multiplicities, consisting of the eigenvalues lambda i's, or I think called, doesn't matter, I goes from 1 to 2g. And in addition, so these are the eigenvalues of the Frobenius, which is acting on our cohomology. And then I want to include the degree v roots of unity. And these we will do for every member of the finite set. I got too many numbers. I think many of you know what is this set. There are two numbers which are redundant here. The number 1 appears at least twice. So I'm saying this makes sense as a set because n is at least 2. So I added all of these roots of unity, so the number 1 appeared n times, I removed twice. And why is this good? Because this set B is the multiset of eigenvalues of the Frobenius. I think that I wrote it this way, and that's good enough. So we are talking about our cohomology with compact supports. And then, still not true, I have to remove the trivial nodule QL, the one-dimensional QL. So the action of the Frobenius will have precisely this set of eigenvalues, so including all of these roots of unity. And then I think that I'm in a position to state the second theorem. So these are just number theoretic things, elementary arithmetic.
For your race here, so here HM is 1, and then you said here HM is a cardinality of 0, so something is bizarre. 0 is trivial in here. I mean, peak, you don't mean, then it doesn't make any sense.
We have the Picard number, which is
Yeah.
given by the value at one of the
P0 is
numerator
trivial on P1, so there are no points.
on P1. Yeah, but we are
So
looking
then
at the general curve.
HM is 1 here. In your
Here?
example, yeah.
Yes, exactly. So we have that HM as a function until when the genus is 0, then the polynomial is trivial. Yes, I agree.
But you say HM is a cardinal, I mean, it's a number of points of peak 0, and peak 0 is trivial. So I
Just
don't
an
understand.
example,
Same,
but-
huh?
An
Well, it
example
doesn't
of
matter.
P1.
It's not important. It's just a question.
Okay, so
I mean, peak has a point, but peak 0 has no point. So, but anyways, it's not so important. And you cannot make peak in the, yeah. Peak has
Okay.
many points, and peak 0 has no points.
Zero. Zero. That's the point.
Trivial on zero, so it's zero.
Zero is zero.
0, okay. Okay, I'm sorry. It's okay.
so you're saying that H.
No, it's okay.
Okay, so I want to just restate theorem 1 in such a way that it will be clear that it is an analog of the Lefschetz point formula, an alternating sum of A numbers. And this theorem would say we have the same sign and the same coefficient, the same expression, and the same coefficients, and the same t's, with one very little change, and that is that the sum is taken no longer over an S, which depends on the finite set S, which may change when we change the base field. I just have to tell you how did we change the T sub m's, and maybe I should have parentheses, so these products have nothing to do with one another. And so we get here a product which is analogous to the Lefschetz fixed point formula. It is a virtual sum of A numbers. And given this type of formula, which is not too difficult to get from theorem 1, it's just a restatement of it. One can restate, okay?
I didn't.
Then we would have a third restatement of the same computation, yet again in a different language, and the statement will be that this number t, which I stated twice already, will be the trace of the Frobenius on a virtual motive on the moduli stack of, maybe I'll give it some the notation. So we have a moduli stack depending on the genus and depending on two integers m1 and m2 over z of triples which consist of our curve x and of two sets S1 and S2 of places so they are, this triple is consisting, so first of all, of a smooth, projective, absolutely irreducible curve X, and so over Z, I guess, and two disjoint sets S1 and S2, they have to be disjoint of geometric points on our curve with cardinalities these numbers mi's. And I need these numbers to be strictly positive. So this is a little bit of unsatisfactory result from the point of view that I would have liked to take a single set, but we are talking here about geometric points, and it might happen that the set will have one closed point which would ramify into 4, and we have not done the number theoretic part of the theorem. So I need to specify two sets to make sure that I'll have at least two closed points. This is maybe a little abstract. Let me write an example.
S1, S2 are FQ rational?
No, they're geometric points, which means over the algebraic closure. So previously we were looking at closed points over FQ on the curve, and we are now base changing. So we would like to have a statement which will be valid for all powers of the Frobenius. And so the points may split.
How is S related to S1 and S2?
S is the union, so we would have that M1 plus M2 is N, and so S1 and S2 will be the geometric points.
And it doesn't depend on the choice?
No. So the question will be to express the number T as the trace of the Frobenius. And if you take a power of the Frobenius, then we would get the fixed points under the higher powers of the Frobenius. Let me just write an example. In fact, we know to write an example only in the easiest case when the dimension is 2. So the question is, what is the motive? And it will be given by the number which is this is wrong what I wrote, let me just correct it. We have that geometrically, so the sum will be m, and m is bigger than or equal to n, which is the cardinality of the set S. So I would have m geometric points. I would like to have them coming from two close points. And so the motive, we can compute it explicitly in the case of dimension 2, and it is given by -1 to the power m, where m is the sum of m1 and m2. It's bigger than or equal to n. And then there will be the rank 1 local system, which is given by the determinant of z to the s. So the top wedge product of this local system. Then we'll have the alternating sum of the wedges. So this is just another determinant. So the H is a local system which is associated with the cohomology of the curve. And the last factor is a sum over the positive integers, again an alternating sum, and we have the Tate motive a tensored with well, again a sum of wedges of j plus 2k of the local system, which is associated with the cohomology with compact supports. So in the way that you read this, it's not so complicated. You get an expression, and each time that you see q, it corresponds to the Tate motive. So q to the j, and so you just see what are the things which come in, and you take the trace of the Frobenius, and that's what you get. So I think that maybe I can give now a slice of introduction. Where does all of this come from? And there is, so the history for me begins with the case of n is equal to 2, and in this case there was the work of Drinfeld, who considered the case, again everything the same, he has a curve, and he looked at the most difficult case, and that is the case where the finite set is empty. This is a very difficult case. I'll try to say in a word why.
Is supposed to have at least 2 elements everywhere?
Right, in our work. So Drinfeld in 1981 consider the case, the analogous question, where the number n was 0. He had to use, the paper is only 1 page, and they didn't have enough paper in Russia in these times, and consequently the subject didn't move for a long time, because for me it was impossible to read the 1 page and be able to do anything with it. He writes a formula. but let me say one more thing. One can also look at the case of two-dimensional representations, and there is the question when the number is equal to 1. This is also a very difficult case, and I've done it. And what is interesting in this case is that you get the same motive. In other words, the motive which is written there, if you take m to be equal to 1, then you compute the trace, and this is the right number that you get. It's very surprising, for me in any case. The motive that Drinfeld gets, it looks completely different. I don't know to explain why. I think that I have a couple of minutes to prove, or just to say a few words on how the proof goes. And the first thing, of course, you cannot prove anything about Galois representations. The only way that you can do anything is to use Laforge and to and translate everything to automorphic representations. And what he said is that that we are looking at irreducible Galois representations of the so not Galois, but really representations of the fundamental group, and then we need to have principal local monodromy at the places in the finite set. And what he said is that there is a bijection between the set of such equivalence classes of representations with cuspidal representations of the group GLN, which are unramified for every place outside of S, and they are Steinberg twisted by an unramified character for every place in the finite set. So this is a big theorem, and one can supply more details, but basically it says that instead of Galois representations, you're going to look at automorphic representations of the group GLN, which are unramified at all places, except at the places at the bad set where we have Steinbergs. Because this is the meaning of the requirement of having a principal, a complete Jordan block at the bad places. This is
irreducible is reflected how here?
Well, question is what you mean by cuspidal. Cuspidal for me means irreducible. Question of definition, but yes, you're right. Irreducible corresponds to irreducible, and if you want to be fussy, then no, we are fussy enough. Then we have one more translation, which is problematic, and it is the inner forms correspondence, or the Lin-Kashdan, or whatever you want to call it. And what it says is looking at representation, automorphic representations of GLN with ramification at least at two places, and this is where the condition at least 2 comes from, is equivalent to looking at cuspidal, but everything is cuspidal, so I'll say irreducible, not one-dimensional representations of, so automorphic, which means that I look at a division algebra, multiplicative group. We are interested here at automorphic representations. So D is a compact inner form of GLN. In other words, a D multiplicative group of a division algebra which is split at all places except at S. At S it is ramified, division algebra. So D is a division algebra unramified except at the places of S where it is a division algebra. It can be a simple algebra, but it is a division algebra. And this puts a condition on the number of places at S. And then, I guess we'll go there. So then, all that's left is simply to compute how many automorphic representations of this group there are. And how do you do that? There are three ways to do it. One way, in fact, all of them are the same. One way is to look, so what kind of representations are we looking at? Those which are unramified at all places outside of S. At S, they're also unramified, but of the compact group, which corresponds to Steinberg representations, but maybe up to a twist, unramified twist. So all that we need to do is look at the maximal compact subgroup of the division algebra and compute the trace of the characteristic function on this space, this homogeneous space. So, maximal compact subgroup of D. So, one way of doing it will be to compute the trace formula. The Zellweger trace formula. This is compact quotient. This is the best introduction to the subject of automorphic representations. You do the compact quotient case. There are no analytic difficulties, so to speak. Another way of thinking about it, if you don't like trace formulas, you can just think about this finite quotient of the homogeneous space by the maximal compact. This is a finite space, and you compute how many elements there are in it.
You need to take care of the adelic center somehow.
Yes. I don't like to do this, and we don't do it. And the translation is, in fact, you're right, you're of course right, otherwise we don't have a finite number here, but the correct translation will be to choose an adelic point, a central element of degree, global degree 1, and take the quotient, not by the entire center, but that's actually what we are doing, and this kills the infinite dimension. So there is the Zellweger trace formula that many people are familiar with, and we have a categorical trace formula. So this computation can be stated, it can be jazzed up to computing fixers in categories. So this is one thing. And as for Drinfeld, what he did in the case n is equal to 2, where the set was empty, he considered precisely the number of unramified everywhere cuspidal, irreducible cuspidal representations of the group GL2. In order to do this, he computed a trace formula which is written in Jacquet-Langlands, but he wrote it correctly, because if you get one number wrong, then the result will be wrong. So he computed everything correctly, and it's a very complicated thing. That's what makes it difficult. In the case that we have a set of cardinality 1, I use the trace formula for GL2, and the question is, so we have a problem here, and that is that if you take a division algebra for GL2, it has to be ramified at an even number of places. The question is, what do I do for GL2 when I have 3 places of ramification? In that case, I don't have a division algebra, but what we do have is a matrix coefficient of the Steinberg. Of course, we don't have a matrix coefficient, we have a pseudo coefficient, and one has to construct the right function that if you plug it in, it picks for you only the Steinberg twisted by an unramified character. So this can be done, and this will give, in particular, the case of one ramified place when we work with the entire trace formula for GL2. So there are many open questions here, I think. For example, the case of n is equal to 1 for higher dimensional representations, I think is very difficult, because seems to me that the trace formula of Arthur is too difficult for to compute with. So this can be a very massive project. For example, the case of the empty set, of course, will be much more difficult, but it seems to be of a different nature just because the motive is the same, at least in this case, it is the same if you have 1 or more places of ramification, and if you have 0 places, the motive looks completely different, because it involves only the Tate motives and it does not involve any of the higher cohomology. So that's about that, and there was I don't have time, I guess, for the exercise that I gave you in the middle, but once you do the exercise, what the exercise said was that as long as the sum of the degrees is 4, we were talking about genus 0, 2-dimensional representation, little n is 2, and the sum of the degrees of the places V in the finite set S was 4. Now one can take and the result is always Q. Then one can twist the situation and get the question of a set S including a single place. When you twist it, it will become 2 or 3 places. And then we have the answer, and under twisting, the number is preserved. So in the case of G is equal to 0, N is equal to 2, and S is equal to 1, there is a purely arithmetic proof of the computation for the motive. You don't need to use the full trace formula. But if you want to get it for all genuses, then you have to use the trace formula, and this is 50, 60 pages, very difficult calculations, and big pain.
So thank you very much. Some questions? Yeah, I have a question. So what about a ranking?
A Rinkin has a beautiful project which has where his question is, we have again the same curve and we have a finite set of bad places, but what he puts there is not, so I put there Steinbergs. What he puts there are tamely ramified principal series representations. So this will be an induced representation from two characters mu1 and mu2 talking locally, and they will be ramified, but not very ramified. There'll be characters on the local field such that the restriction to the units will be trivial on the on congruent to 1. So he puts there tamely ramified characters, and then again you have finiteness of the number of Caspidal representations on GL2, and he has a geometric way, purely geometric way, to count how many local systems there are.
Who is this?
Arinkin.
In fact, the link was.
So
I started thinking of this because of Arinkin.
Arinkin was, I believe, a student of Drinfeld, and I don't believe that he wrote it up, but he computed the number of local systems up to equivalence fixed by the Frobenius, in other words, of automorphic representations, which are unramified at all places, and the ramification is a finite number of places where you have tamely ramified components.
But he did it geometrically, or did
Purely
he
geometrically.
Yeah.
He does not speak the language of automorphic representations.
And, why?
That's for GL2.
I believe that he looked only at the case of GL2. So a natural question, which is, I haven't had time yet, but I do intend to look at if you can use a trace formula to count these kind of objects. But Arinkin has a purely geometric approach, and Delin has interesting comments about it, which you got also. So, and I should mention there is also a paper of Dick Ross where he is counting over number fields automorphic representations for a general group which are unramified at all places, and at finite number of remaining finite number of places he fixes the ramification usually to be Caspidal components. But what made the work of Drinfeld so interesting is that he used the full power of the trace formula. So what we did with at least two places has more geometric flavor. We have not only the computation, but also the translation to local systems and to the language of motives.
So,
Sorry?
why do you count this specific type of representation with a single Jordan block and so on? Do these build in some way? Do you generate other?
Yeah, because of Eisenstein.
Steinberg. It's
Steinberg.
it's because
of Steinberg. Well, it's not
no. The answer, to be honest, is that I compute only what I know to compute. Other things which I do not know to compute, I think that I have nothing much to say about. But so it started. I come from automorphic representations, and there I know that you can compute with a trace formula. And if you have unramified components, it's easy to compute. You plug in the characteristic function of the maximal compact at finite number of places. The only thing that you can say is, do you have a pseudo coefficient or do you not? If you don't, tough. So we work here with the Steinberg. Not really the Steinberg, but Steinberg twisted by any unramified character. And either you have a division algebra or you have pseudo coefficients. You can write it out. I intended. This is an interesting point. I have one line, not 3
There's
minutes.
another question, but go ahead.
So the answer is I can compute it with the trace formula, and then we can translate it
So
to
that
motives.
means these are somehow reckonable down, uniformly reckonable down representations.
Yes,
And therefore you can expect a kind of regularity.
yes.
But at the moment there is no insight how building decomposing representation in such blocks and other kinds of, I do not know, how you could get over this and describe more general representation.
No, you have Lafog, and he gives you a one-to-one dictionary between Galois representations and automorphic representations. You can do analysis on the automorphic side, then you can state what you want in your language, and then everybody is happy. Now, on the Galois side, you can do many things. You can take products of representations, you can take symmetric powers, whatever. We can just compute these numbers on the automorphic side by plugging in test functions and doing the computations.
There comes out something like this.
And so, what comes out is the case of full Jordan blocks at the bad places. So we have principal monodromy. The case of a Rinkin, I believe that it can be done. And then it will give non-principal Jordan blocks at a few places, and it will be just a reducible representation on the Galois side, just sum of two characters. I believe that this can be done. But you can do more. You can put at the bad places cuspidal components, so irreducible Galois representations. And this is more difficult from a certain perspective, but it's easier from an analytic point of view because you have a matrix coefficient of cuspidal representations. Technically it's easier. So the less ramification you have, the more difficult it is. And if I can choose one theorem that I would be able to prove, I wish, if somebody hears, the case of GLN and no ramification. This is the utmost that from analysis that we could do. This is very, very difficult.
Asher?
So, one natural question is maybe have you studied the asymptotics, say as n goes to infinity, as maybe q goes to infinity? I mean, what does this formula look like?
It's an interesting question, and I don't know the answer. I haven't thought about it, but the answer is, in principle, should be squeezed out from the motivic description, but I haven't thought about it. Yeah.
Is there some kind of Chebotarev type theorem that comes
You
out
mean
of
to
the-
increase the dimension n, little n?
Yeah, I mean,
or-
that's maybe not so clear what to do, but maybe as q goes to infinity.
The higher powers of the Frobenius. So the formula would say that it is like a Lefschetz fixed point formula. So you have a virtual linear combination of powers of these lambdas. So the answer, in fact, is the same as in the fixed point formula, the Lefschetz formula, that you have no limit because you have just something like this, and so you have some finite sum of some Weil numbers with some integral or whatever coefficients, and it makes no sense to raise m to higher power because it won't have a limit. But it looks like this for every power of the Frobenius.
And then finally, from the formula, it's amazing that in the case for the exercise you wrote down that the answer is divisible by q.
Equal to q.
Equal to q, but in particular divisible. I mean, no, it seems like no factor in that formula is at all divisible by q.
Yes.
Or it, you know, naively.
Yeah,
so there
we
must be
had to
some
check.
amazing cancellation.
It's not clear that you get an integer.
Well, that too.
And so what's written on the right is some complicated expression with a denominator. It's obviously a rational number, but it's not clear that it's an integer. We had to see that it's an integer. The exercise, it's simply case by case. You have 3 plus 1, 2 plus 1 plus 1, 2 plus 2, etc. In each case, you have a different little calculation. And they all come out to be the same thing, which means that it's independent of the field extension. And consequently, you can twist and you can deduce the case of S being a singleton. Otherwise, it would not have worked.
And then in that case, do you know, I mean, you know the action of, you know, the actual Galois action on the set of order Q? Somehow, if you knew that this number was not divisible by Q, you know something very nice about the kind of field of moduli of this stack. But somehow, it's amazing. Yeah.
I don't know. I don't know.
I hope there are no longer any questions for this room. So thank you very much.